The central limit theorem. Imagine you have a population with a certain characteristic. It could be height, test scores, or anything measurable. Now, the central limit theorem tells us something fascinating when we take repeated random samples from that population. First and foremost, regardless of the shape of the original population distribution, as we take more and more samples and calculate their means, the distribution of those sample means tends to follow a normal distribution. This normal distribution is often referred to as the bell curve. The bell curve, or the normal curve, is characterized by its metric shape with the highest point or mode located at the center. It's unimodal, meaning it has only one peak, and it is defined by its mean and standard deviation. Roughly 68% of the data falls within one standard deviation of the mean, 95% within two, and 99.7% within three standard deviations. Second, the largest our sample size are sufficiently large, the closer the distribution of sample means resembles a perfect normal distribution. In other words, the more data we have, the more the central limit theorem kicks in, providing us with a reliable and predictable pattern. By convention, we consider a sample size of 30 to be sufficiently large. When n is less than 30, the central limit theorem doesn't apply, and the sampling distribution will follow a similar distribution to the population. Third, it allows us to make powerful inferences about the population based on our sample means. We can calculate probabilities, make predictions, and draw conclusions about the characteristics of the entire population with a high degree of confidence. To sum it up, the central limit theorem provides a bridge between the characteristics of a population and the reliability of the sample data. By understanding how sample means behave, we gain powerful insights into the underlying population, facilitating sound decision-making.